This problem says find f of g of x and g of f of x. And here's f of x is the cube root of x squared plus 1, and g of x is x cubed plus 1. So a refresher on notation, when you see something like this with a small circle, these two are functions and this is the variable, and f of g of x is equivalent to the way I said it, which is the input to the function f is the output of the function g if the function g takes x. And we'll do an example right now. So in this case, the inner function is g, so everywhere I see an x in the outer function, I need to substitute it with g. Now see how f is the cube root of x squared plus 1. I need to replace the x with x cubed plus 1. And you see how it's squared. So I put squared plus 1, and then the square root. So you can see how it is. Oops. Now we'll see if I can simplify it, or if it's just better left. You know the binomial theorem, x squared is this squared, so x cubed squared plus 2, x cubed times 1 is 1, plus 1, and then this plus 1 is plus 1. Now this is x to the 6th plus 2x cubed plus 2. So this is a little bit less complicated than that. So I'll go ahead and put, oh, you see what I forgot? I almost forgot that. That would have been a wrong answer. Gotta pay attention to everything. Okay. Hopefully I didn't make any other mistakes. Now g of f of x, oops, means everywhere there's an x in this function, I replace it with this. I'm going to put some parentheses. I'm going to write the whole function. Now, it's cubed in g of x, so I put that right there. Now this one, what simplification do you see? This is a cube root. This is raised to the 3rd power. What happens? They cancel out. And so what's left is what's inside. X squared plus 1, and then this plus 1, which is equal to x squared plus 2. So f of g of x is the cube root of x to the 6th plus 2x cubed plus 2, and g of f of x is x squared plus 2. So you can see they're frequently not equivalent, so order does matter. This problem says find f plus g, f minus g, fg, and f over g. And here are the functions. F of x is 3x squared, g of x is 1 over 2x minus 3. So this notation means the sum of these functions and difference and product and quotient. So we just simply perform the operations. So the first one would be, you take f of x, 3x squared, and you add if there are any good simplifications, we could convert this into one fraction, but I'll just leave it like that. If you want to convert this, you could just do that and put your answer. If your teacher likes things to be a single fraction, if there are multiple things, then that would be a good thing to do. And f minus g would be 3x squared minus 1 over 2x minus 3. Multiplying f and g together would be 3x squared times 1 over 2x minus 3, which is 3x squared over 2x minus 3. And f over g equals 3x squared. And what I'm going to do is invert and multiply. So if g of x is 1 over 2x minus 3, 1 over that is just 2x minus 3. And for this one, I will simplify. This is 3x squared times 2x is 6x cubed minus 3x squared times negative 3, or times 3 because I already put the minus, 9x squared. Okay. This problem says find f of g of x and g of f of x, where f of x is the square root of x squared plus 4, and g of x is 7x squared plus 1. So for the first one, let's first replace every x in f of x with 7x squared plus 1. So this is x squared, so this is going to be equals, okay. I like to write it starting with the x's and work my way out, especially when I'm having to allocate space for each x. And you have to make a judgment call. Sometimes you want to work it out on paper, whether or not you want to expand this and see if it's going to conveniently work out. I think I'll just leave it at that. Now g of f of x, I'm going to do everywhere there's an x in g, I'm going to replace it with, and I think I see where it's going to get nice, meaning in this case, the square and the square root cancel out, so you have 7 times x squared plus 4 plus 1, and it's worthwhile to factor the 7 over this, so you get 7x squared plus 28 plus 1, and combine the 28 and 21, 7x squared plus 29. it's good to look back over and see if you can tell if you missed anything. Sometimes it's worth a good 5-10 minutes to go retrace your steps, see if you forgot something. Hopefully I didn't forget anything, but I think that's good. This problem is another composite problem, f of g of x and g of f of x, with f of x is 1 over 3x plus 1, and g of x is 2 over x squared. So let's find f of g of x. Everywhere where there's an x in f of x, I'm going to replace it with g of x. So you got 1 over, this time I'm writing f of x first, 3, instead of x I'm writing 2 over x squared plus 1. Now let's see if we can simplify this. 3 times 2 is 6, so this is 1 over 6 over x squared plus 1. We can see if it will look nicer if we combine this fraction in the denominator. This is the same as 1 over, multiply the top and the bottom over here by x squared. This is 6 plus x squared over x squared. Now if you have 1 divided by a fraction, you can bring the fraction up and just flip it. So this is equal to x squared over 6 plus x squared. If I haven't made any algebraic errors, that should be f of g of x. Now, g of f of x, you take this everywhere in this function. So you start out with g, you got 2 over, now this is 1 over 3x plus 1 squared. In this case, we can do this. If you have a fraction, a over b squared, what is it equivalent to? It's equal to a squared over b squared, right? You can always take a exponent into the numerator denominator. 1 squared is just 1. Now you don't want to put the squared on each one, you got to keep it as a unit. So 3x plus 1 squared. What would you do at this point? Before I do what I'm going to do, think, what would you do? If you're dividing by a fraction, you bring the fraction up into the numerator and flip it upside down. So you got 2 times, well, 3x plus 1 squared over 1 is just 3x plus 1 squared, right? Now we can expand this binomial. Might as well. Let's do 2. 3x quantity squared is 9x squared, plus, because there's a plus right here, what's 2 times 3x times 1 is 6x, plus, and 1 squared is 1. You see what I just did, right? You know that a plus b squared is equivalent to a squared plus 2ab plus b squared. It's just a particular instance of the binomial theorem that I've used so often that I have it memorized. Now it's easy to distribute the 2 in. So this is equal to 18x squared plus 12x plus 2. Once again, if I've made any errors, I can go over a review of each step. I always encourage people to review their steps, but we don't want this video to be 6 hours long. If I have an error, that's embarrassing. This problem says find f of g of x and g of f of x, where f of x is 2x squared plus 5, and g of x is 4 minus 7x. Let's find f of g of x. What do we do first? You can either write the whole inner function, or you can start to write the outer function. When the inner function is pretty big, I often start with that. So I write 4 minus 7x in place of x, and I look and I try to remember, include that square, put that 2, put that 5. At this point, you can make a judgment call if you think that expanding this binomial is going to be worthwhile. How about this time I don't? Then g of f of x. Now I'm going to insert 2x squared plus 5 everywhere there's an x in the outer function. I'm going to start by writing the g of x first, 4 minus 7, and then x is 2x squared plus 5. Now this time, I'll go ahead and distribute the minus 7 over the 2x squared plus 5. So we've got 4 minus 7 times 2x squared is what? Minus 14x squared. Minus 7 times plus 5 is what? 28, 35? Yeah. Minus 35. There are some likes that we can combine. 4 minus 35 is negative 31. So I can just put negative 14x squared minus 31. And if you wanted to factor out the negative symbol, you can put 14x squared plus 31. Look over, see if I made any glaring mistakes. Not that I notice. And of course, go over with a fine-toothed comb, maybe solve it again a couple times later offline. This problem says find f plus g, f minus g, fg, and f over g when f of x is 7x to the 4th plus x squared minus 1, and g of x is 7x to the 4th minus x cubed plus 4x. Now, instead of trying to do this on the spot, I paused the video and did it very slowly and very carefully. I encourage you to also do things very carefully when you're doing problems with lots of terms. I find that for me, the most often mistake is when I'm adding or subtracting a quantity in parentheses and having to manage the signs of the terms. Also, by the time you've got 5, 10, 15, 20 terms, and then when you get to the step where you're grouping like terms, you just got to find a good bookkeeping way of keeping track of what you've already hit and what you've not yet hit. Some people like to slash out terms that they've already done. Whatever works best for you, or whatever you find works best. Anyways, this is the final answer that I got. Here's f minus g. And you see we had to change the sign right here, which changed the signs of these terms so that the 7x4s canceled out. Also the signs of the other terms that were here changed. And here's the product of f and g. This was so far and probably the most tedious of all, but it's good practice to have good methods of keeping track and looking for like terms to group together. This was my final answer. And surprisingly, the division problem seems to me to have been the easiest of all, because I don't see any further simplifications. So after this type of problem is usually when I would definitely want to take a break to relax my eyes before moving on to the next problem. This problem is a composite problem that says find f of g of x and g of f of x, where f of x is x squared and g of x is 1 over x squared. So let's do f of g of x first. Okay, first we have g of x, which is 1 over x squared, and f of x says to square it. So this is 1 squared over x squared squared, which is 1 over x to the 4th. 2 times 2 is 4. Now, g of f of x we start with f of x g of x says 1 over that squared, which happens to be the same exact function. So sometimes composite functions are the same both ways. This problem says find f of g of x and g of f of x, where f of x is x cubed and g of x is x plus 1. So pause the video, see if you can solve this one. Remember, g of x is x plus 1. F of x is x cubed. You can leave it at that, or you could expand it. I personally would leave it at that. Now, g of f of x you take x cubed and substitute it for x in g of x. So this is x cubed plus 1. This problem says find f plus g, f minus g, fg, and f over g, where f of x is 2x cubed minus x plus 5, and g of x is x squared plus x plus 2. Again, after you've done one or two of these problems, they're not hard, they're just tedious, so you got to be extra careful. So I like to draw parentheses around the second function, even if it's obvious that they're all going to be added, and then you find terms that cancel out, and this is the final answer that I got. And with the difference of functions, I changed this to a minus, which changed all these previous pluses to minus, and this is the answer that I got. Here's my answer for the product, FG. And I hope that even though this is tedious, you are actually doing it on paper, because actually doing the work helps to learn it. So my strategy is to start with the first term and multiply it by each one of these, then move on to the second term and multiply it by each of these, and the third term by each one of these, and then find the like terms, group them. This is my final answer. And here's the quotient of the two functions. I didn't find anything to factor out. I actually performed a synthetic division. That's a technique that I encourage you to look up in another video. Polynomial division is also known as. This problem says, prove that every function with the domain over the whole set of real numbers can be written as the sum of an even function and an odd function. So these functions are not even specified, they're just saying that every function. So how would you begin to approach this problem? Just to illustrate, say the function looks like this. How do you prove that this function, just as an representative case, could be written as the sum of a function that is even, that is symmetrical about the y-axis, and an odd function which is symmetrical at the origin? So just to state it again, let some function h of x have the domain from negative infinity to positive infinity. So for all x in the set of real numbers, h of x exists. Now, keeping things perfectly abstract and just acknowledging that h of x exists, suppose it has some value, a. We haven't said what a is. And suppose h of minus x is equal to b. And b or a could be greater or less, or they could be equal to each other. We're just drawing them this way for graphical purposes. So we're given that these exist since the domain of h is the whole set of real numbers. And we're saying that a and b could be any value, because the function could take on values within a bounded region, or they could be, the range of the function could be the whole set of real numbers. It doesn't matter, because there is an a and there is a b, and the distance between them is something, could be 0, could be negative or positive, depending on the signs of a and b. But we can just assume that they are some numbers. Now, every range, even a range of 0, let's say h of x equaled h of minus x. In this case, the midpoint between h of x and h of minus x, if both of them were a, it would be a, yeah, the midpoint would be a in this case. In this case, where they differ by some amount, do you agree that the midpoint between this would be a plus b over 2, right? So it has some midpoint value. Okay, I'm going to write that on this side because now if they are both equal to each other, h of x and h of minus x, then the midpoint is a, and the difference between the midpoint and h of x would be 0, and the midpoint between h of minus x and the midpoint would be 0. But in this case, let's call a plus b over 2 the midpoint. Let's call that some number c. Now the distance between the midpoint and the upper value will be some value d. And because this is the midpoint, wouldn't you agree that the distance between the lower bound and the midpoint would also be d? So we're keeping this all abstract. We're not supplying any numbers. So look at this and think about this. Think about the definitions of even and odd functions now before we move on. Maybe go back in your textbook or your notes. Okay, the next step is I've just written this right here, which is an algebraic form of saying what we have in this diagram. We have C being the midpoint between B and A. So h of x is equal to C plus D, and h of minus x is equal to C minus D. Did I say that right? A is equal to h of x, which is C plus D, and B is equal to C minus D. Now, the next thing we're going to do is write down the definitions of even and odd functions. So what I wrote up here was the definition of an even function. For even functions, f of minus x is equal to f of x for all x on the domain of the function. And for odd functions, g of minus x is equal to minus g of x. So think about that. If we were to write this, let f be an even function so that f of x, f of minus x, and f of x have the same value, and let g be an odd function so that g of minus x equals minus g of x. I'm going to erase some stuff and then we'll move on. So there's no reason we can't define some functions so that f of x equals c, and we let f of x be an even function so that f of minus x is also equal to c. And we could define some function g of x that is odd and say that at x, g of x equals d. And if g of x is d and it's odd, then at g of minus x, it'll be minus d. So if we define these two functions, then h of x, which is equal to c plus d, now at x, we're saying that c is equal to f of x, and at x, g of x is d, then h of x is equal to f of x plus g of x. Now what is h at minus x? It's equal to c minus d, right? What is c? C is equal to f of minus x. And see how how h of minus x is c minus d. Look what minus d is. Minus d is g of minus x. So we plus g of minus x. Let me write that more clearly. See, h of x is equal to c plus d, which is f of x plus g of x. And h of minus x is c minus d, which is f of minus x plus g of x. So they're both equal to whether it's x or minus x, h is always equal to f plus g. So without specifying the types or the details of the functions, we can say that we can create some function so that it is the sum. We can create even and odd functions so that they add up to any type of function. And if d, let's say h is an even function, then we just make the odd function d 0. That was one way to prove it. If you have a different type of proof, I'd like to hear it in a comment.